to the where the x is, and you plug in the 2 to the y.
Good, we need the slope, right? So the slope is dy dx. We need the slope at the point 1, 2, so we put 1 in for x and 2 in for y. And that gives us 4. Any questions about that so far? Use the tangent line to approximate the value of f of 1.1. Plug in 1.1 into the tangent line, into the x value, into the tangent line. Quick question. Can you solve this differential equation? No. No. Why not? You can't separate the variables. They're added together. So you can't divide by y, you can't multiply. You're stuck until you get to a class called differential equations in college, which comes after step 2. So I can't solve this. So what we're doing right now is a way to approximate values on the original curve, even though we don't know it. No, it's EULER. 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 It's pronounced Euler. It's weird. Okay, so I know it looks like the weird things you know when you're teaching calculus, how to pronounce it. Okay. Use the tangent line to approximate the value of f of 1.1. So I'm going to put 1.1 in for x. And I'm going to find that f of 1.1 is approximately, and make sure on the AP exam you don't say f of 1.1 equals. It's not equal to, it's just an approximation based on a tangent line. Tangent lines get close, they don't give us actual values. So, what is f of 1.1? Someone with a calculator. Actually, 2.4. Yeah. Any questions so far? Write a new tangent line at the point you found in part B. Can I do that?
Sure.
Sure. Y minus 2.4 equals, what is that? 2.2 plus 2.4, which is 4.6. Is that right? I'll check it out at 4.6. Stop calculating. Is that 4.6? Slope at this point. Use the tangent line that I just found to approximate f of 1.2. Can I do that? Minus 2 and where x is, right? And so I get 0.1, 2.86. Any questions so far? This is tedious, but it's just tangent lines, isn't it? Now we are going to get a little faster at it by using a table, but I want you to know where it comes from. So if you got stuck, you can go back to just using tangent lines. Hey, any questions so far? It says to continue this process until you've approximated f of 1.4. Well, how many more times do I need to do this to get there? 2 more times. I need to find f of 1.3 and then f of 1.4. Right? So I'm going to do y minus 2.86 equals, calculator, tell me what it is. Thank you. 1.2 is 2.86. 1.2 is x, 2.86 is y. So 2.4. Any questions? questions so far? So I can find out 1.3. 0.526 at 2.86, so 5.26. And that would be 8.02. Calculator, so it's it's 3 point what? Okay. Okay, any questions? Does everyone know how we're getting that? Any questions about it? Okay, that's that 1.3. So now I can do y minus 3.386 equals m. What is m? Something with a calculator.
5.96.
5.986. So then I can do what I was trying to do the whole time. Find out 1.4 plus 0.5986.
3.95.
3.985. Okay, so now let me tell you where this comes into play. Remember when we very first learned differential equations, how we talked about their usefulness in the real world? I told you about a professor I had who did all of his research in MRI brain imaging. The mathematics behind that was differential equations. We talked about how there are some differential equations that are unsolvable so far. Remember, there's one that you can get $1 million if you solve it. Remember those conversations? Well, in the meantime, until they can be solved, there has to be a way to approximate the solutions. And Euler's method is one of those. Now, we use step size of 1/10. Could you get better than that if you wanted to? You can imagine a computer program could run Euler's method. Have y'all ever used Excel? Dragon, use that? So you can imagine a computer program could be written to use Euler's method in teeny tiny increments and get pretty accurate. And there's even a way to figure out the error on Euler's method. We're not going to do that today. But Euler's method can give you a very good approximation for a function value on a differential equation that we cannot solve. And it's using local linear approximation routine. That's what we're going to learn how to do today. So, Euler's method is used to generate numerical approximations for solutions to differential equations. The things that it's necessary to know, they word it differently, but you need to know x, y, and m, right? It's necessary to know an initial point and a rate of change. Euler's method uses local linear approximations at successive steps to approximate these solutions. Now, we did it probably the way Euler did it the first time on the first slide. We just cranked out tangent lines over and over again. You can set this up a little nicer to kind of do some adding and subtracting a little faster. But what you're doing is what we did on the bell ring. You are doing multiple tangent line approximations. Luckily, on the AP exam, they ask you to do 3 or 4 repetitions. So they don't make you do this 100 times, which is probably what's useful in the real world, is really tiny approximations. They don't make you do that. They would assume a computer program will do the cranking out the math part of it. But they just want to see that you understand the process. So, could you use what we did on the bell ringer every time Euler's method comes up? Yes. There's nothing wrong with that. I am going to show you a little table setup that kind of streamlines the process. I have mixed feelings about tables because the chances you remember how to do the table in May Who knows? Chances you know how to do a tangent line in May, you better, right? So hopefully you could do the tangent lines in repeated. So that's why I wanted to show you the bell ringer, even though a textbook wouldn't show you that way. If you get stuck, that's how you do it. You just go back to tangent lines. That is the understanding behind Euler's method, is multiple tangent line approximations. Okay, starting at the initial point, the next point is about using this formula. Looks kind of scary. X is the first x plus delta x, or dx, change in x. The y is the first y plus the derivative at xy times the delta x. Fancy way to rewrite finding the next point using a tangent line. Subsequent points are found doing the same process. Now again, this is a fast way to do what we already did on the bell ringer. Faster way. So you're going to take your original x and add your change in x. What was our change in x on the problem we did on the bell ringer? 0.1. We were going up a tenth every step. So the delta x, or the dx, is the change in x, which was 0.1 on our problem. And then we're going to say the y value is calculated by using the initial y value plus the derivative times the change in x. Isn't that what we did already? Using a tangent line. So again, if you prefer the bell ringer option, part of me does. It's not quite as streamlined as what I'm about to show you, as a textbook would show you, but it always gets you the right answer. And sometimes there's perks to that. So this is how my textbook would show you how to do Euler's method. And let's talk about the actual wording. I modified this problem into the bell ringer, to where you didn't know it was an Euler's method problem, but this is the bell ringer and how the problem was originally worded. It says, given that dy over dx is 2x plus y, and f of 1 is 2, use Euler's method to approximate f of 1.4 using 4 increments of equal width. So this is how that question would actually be worded using Euler's method. And I'm going to show you how to use a table like this. If you would rather just do tangent lines, do tangent lines. I have no problem with it. The first thing we need to figure out is the increments of equal width and how we work with that. What is the x value that we currently know? 1. And where do we want to get to? 1.4, how far away is that? 0.4 units. So if I want to do increments that are equal width, then I need to go up by 0.1. Any questions about that? So that's the first thing you need to figure out, is what you're going to go up by. That's going to be your change in x, your dx.
Undefined or zero. Crap. I have to do this whole thing over because I love
Now this table really slowly breaks down what this says back here. Y, you could just skip and find y1 and not find delta y if you wanted to. Delta y is just change y. Delta y is this piece here. It's the derivative times the change in x, the slope times the x, which will just give you the change in the y. So this table kind of breaks it out probably more than you would have to. You could just skip to find a new y. X is currently 1, y is currently 2. dy dx is the derivative at that point. What is the derivative at the point 1, 2? 4. So the change in y is dy dx times dx. Wouldn't that give you dy? You multiply dy over dx times dx. Dx would cancel. And so you get 0.4 for dy. There's a lot of space there because it wants you to work that out, but you can. X plus the delta x would be 1.1. Y plus the delta y would be what? Look back at the bell ringer. What did we get for our first? Okay, you see how this is really just, to me, almost overcomplicating a tangent line. So again, if you prefer what we did on the bell ringer, that is always an option. You'll never see a textbook do it that way. They will always set up Euler's method as a table. But again, I like understanding more than memorization, and I think you understand tangent lines. We're just doing multiple approximations of tangent lines. Any questions so far? So, that's my new point. And I'm going to find dy dx at that new point, which would be, we found that on the bell. What was it? 4.6. We're going to multiply 4.6 times 0.1, which is 0.46. X plus delta x is 1.2. Y plus delta y is 2.86. Is that right? Yes. 2.86. And it is streamlined. This is nice on your brain on how to, you're adding and you're not having to add over and all that stuff. So there's some nice things about the table. Remembering how to set it up is the thing that would be more of a problem in May. So that's where if you prefer tangent lines, I have no problem with that. Does this make sense? Yes? I like the way I taught that at the beginning. I like doing the tangent lines first. I think it makes sense. Alright, 1.2, 2.86. My dy over dx, 2 times 1.2 plus 2.86 is 5.26, is that right? 5.26 times 0.1, 2.526. So at each point we're using the new slope to get a better approximation. We're not using the same slope from the beginning. That way we come up with new tangent lines at each approximation. So the tinier your increments, the better approximation you get. 1.3 and 2.86 0.86 plus 0.526 is 3 point something. 3.86. 3.86. You do not have to do this without a calculator. Euler's method is going to be something where you can type it in. He doesn't know Euler's method. Alright, 1.3. 3.386. What's the slope?
That's right.
Times 0.1 would be 0.5986. And plug in, or add 3.386 plus 0.5986, and what do you get? That is how you do Euler's method. Okay, any questions about that? Okay, perfect. You're not a math. Do what? It was always Euler, you were just pronouncing it.
So nobody ever just told us.
I think that's like a qualification to be a math major. You have to learn how to pronounce Euler appropriately, or
French.
I think he is French.
That would make sense.
Okay. This might be a real AP problem. Maybe, possibly, could have been. Looks like it. But from here on out, we're just doing examples. You've learned Euler's method already. So let f of x be the particular solution to the given differential equation with initial condition f of 0 equals 2. Use Euler's method starting at x equals 0 with 2 steps of equal size, which lets you know you're not always going to have to do 100 approximations. So we only have to do 2 steps to approximate f of 0.6. Now what does that mean each step size is going to be? 0.3. Everyone agree? To get from 0 to 0.6, with 2 increments, I'm going to be going up by 0.3. Show the work that leads to your answer. You can use a table. You can use tangent lines. Nobody cares which one you use. Which one do y'all want to use, just out of curiosity? I've skewed your thoughts up.
No, it's just easy to do this with drop example.
Yeah, and so memorize it in your thought process. We already have one that works perfectly good. I can feel about it, but y'all kind of get skewed from my opinions. Y minus 2 equals -1 times x minus 0. That is my first tangent line. Agree? What am I going to plug into that tangent line? -3. -0.3. 1.7. So f of 1, no, f.3 is approximately 0.7. Oh, 1. Yep, 1.7. So that's step 1, right? We wanted to do 2 steps. We're going to do that again. Y minus 1.7 equals the slope. I'll have to find that out. Times x minus 0.3. you notice I only had to do 2 steps. 0.3 times 0.7 is add 1.7 to 1.449. Is that what everyone's getting? Like I said, I believe this is a real AP problem. So where does it go from there? So we approximated it. Then it says find the particular solution to the differential equation and use your solution to find f of 0.6. So now we're doing a comparison, right? The real value to the approximated value. On the problem on the slide before, I couldn't do part B, could I? But on this one, can I? It doesn't have a y on the right, so it's very easy to separate the variables. Grant, this is what easy differential equations look like. Non-logistic differential equations. Okay, and so I differentiate. So I get y equals what?
1/2 x squared minus x plus 2.
Okay. Now what? We feel like we just went back in time. Simplicity of the differential equation. Put 0 in for x, 2 in for y. So c is 2. So y equals 1/2 x squared minus x plus 2. So that's f of x. So what would f of 0.6 be? Use a calculator. Which 1.12 half of that. Say that again.
1.58.
Yeah, we'll try that.
Not quite there, right? Is it pretty close though? Remember, how big of a step did we do? Pretty large step. We did a 3/10 of a step. Again, if you can imagine in the real world, you could do steps because you've got computers on math for you, right? So you could do a step of 100 if you wished, right? And do a bunch of steps, 300 of them. Again, we're using by hand methods, so we wouldn't want to do that. But, so one more. I feel pretty good about Euler's method. Monday will work after your gateway. And we're not learning anything new on Monday. Just take a look at it's just a single page and there's one that's we can 4 of those over. Exactly. One table. Use Euler's method to approximate the value of 2.6. This looks very AP-esque, doesn't it? Yeah, and so they're really just testing to see if they're tying your hands on. If you had a calculator program that did Euler's method, they're tying your hands on it, right? Because they don't actually give you the differential equation. They don't actually give you. So this is how they do things like that. So, is it any harder to us? No, we have our first length of 0.32, right? And we have our slope of 0.4, and we just do. Now, what do you notice they're doing instead of going up?
Going down.
Does it matter?
No.
It doesn't matter, does it? What is the change in x if you're going down? It's negative. Is that a problem? If you're doing tangent lines, you do nothing different. If you're doing the table, you will notice that your delta x is negative, but other than that, okay, so y minus 2 equals 0.4 times x minus 3. I'm going to approximate the y value at 2.8. Negative 0.2 times 0.4 is negative 0.8 plus 2, 2.8. Let's check that. 2.08. Oh, yeah. You're right. 1.2. Yeah. So that's